All right, welcome back, subscribers, to another fantastic episode of Science with Surback. Today, what we're going to be talking about in AP Chemistry is Section 15.6. And Section 15.6, yet again, goes one step further into that equilibrium constant expression and that equilibrium constant. Now, there's a few specific objectives that we have with this particular section of AP Chemistry. So, the objective that we have is calculate the reaction quotient, Q, and by comparison with the value of Kc, determine whether a reaction is at equilibrium. If it is not at equilibrium, predict in which direction it will shift to reach equilibrium. So what we're going to do, we're going to go one step further again with K. And so we start out here with a review of what K is. So with K, there is two options that we have. Option one is we can have a large K. And so if we have a large K, what that means for us is that we are going to have a system of equilibrium where the products dominate, or the substances at equilibrium are mostly the products. All right, so again, if we have a big K, hey, that means we mostly have products. Now, on the flip side, the reverse is true. So if we have a small K, we are going to get a system of equilibrium that contains mostly reactants. Now, the reactant side, typically in equilibrium systems, is going to be referred to as that left side. So what the whole thing with this K, why we need to have a knowledge of big and small Ks, is we can do a couple of things with this K. Number one, what we can do with this is we can predict the direction So what we can do here, we can predict, this is probably the major thing here, we can predict what direction this equilibrium system needs to shift to be able to reach that equilibrium. And then number two, we can calculate, if we know knowledge about this K, that R should not be there, we can calculate the equilibrium concentrations. And again, these two things is what we can do with that equilibrium constant K. And so we get down here to how can we know, or how do we know which way this equilibrium shifts? And we get to this reaction quotient. Now the reaction quotient is defined as the number that is obtained by substituting reactant and product concentrations or partial pressures at any point during a reaction into a equilibrium constant expression. So I'm going to pause and write that down. All right, so here is that definition written out. Now, with Q, it's going to look very, very similar to K. The only difference, and it's not very clear in this definition, but the only difference is that we are not necessarily at equilibrium. In fact, most of the time, we're probably not at equilibrium. Now, if we compare it to K, we can say, hey, the equilibrium needs to shift back to the left and or back to the right, depending on the scenario that we'll state down here in a second. Now, for our reaction quotient, like I said, it's going to look really, really similar to what we have dealt with before. So in this, I'm just going to put a general reaction. And RXN just stands for reaction. And in this general reaction, we're going to have substance A, substance B go to equilibrium, and we produce substance C plus substance D. Now, our reaction quotient out to the side here is just going to look like this. We're going to call it QC, and again, just like the equilibrium constant expression, on top, we're going to put the concentration of the products, so C to that C coefficient, D to that D coefficient, and then on bottom, we are going to divide it by the reactants. Again, a generalized reaction, but we have the same exact format as the equilibrium constant, except we no longer have K, we have Q to represent that reaction quotient. So if we compare KC to QC, or if we put it in layman's term here, if we compare the equilibrium constant to the reaction quotient, we can do a couple of things. So number one, our first option is Q is going to be equal to K. If this happens here, the system is at equilibrium. Now, our other two options, or our first of the two options, Q can be less than K. So Q is not as big as K. What happens here is the forward reaction must occur until we reach equilibrium, in which Q equals K. What this means, what you'll commonly see when Q is less than K and we have to have that forward reaction, is you'll see this expression is the equilibrium must shift to right, or it must shift to that side of those first products that we see. Now, just the reverse is true if we get to a scenario where Q is greater than K. This is just the opposite of the thing that we just wrote here. So in this case, the reverse reaction must occur to reach equilibrium. Now, what you'll see in section 7, in fact, you'll see if we have to have the reverse reaction occur, this thing is going to be called shifting to the left, or shifting to those original reactants. So we have a few things here. This is a lot of definitions, and now we can finally get to looking at what does all this stuff mean. So I'm going to shift gears here, and I'm going to get the next sheet of paper out. All right, so in this case here, what we want to do is this. We have our Kc for this particular equilibrium expression, and that Kc is 50.5. Now, we want to predict the direction the reaction needs to proceed if we have these particular conditions. Now, these things right here, I'm going to touch on this again, but we can plug it directly into our QC. So what we're going to do is this. Our QC is going to be our products, which is HI. Now, I know I've been writing this as concentration, and these are listed as gases. The reason I'm doing that, the reason I'm putting these things in brackets, is because what we have is concentration, molar. So whenever you're given molar, always write it with brackets, and you don't need to worry about that pressure business. But this thing right here, HI, is raised to the second power, and it's divided by H2. Because it's a product, it's raised to the first power because of the coefficient of 1, times I2, which it's raised again to the first power because it's the coefficient in front of I2. Now, what happens here is this. All I'm going to do right now is I am going to insert the values for each of these substances. So, right here for HI, the concentration that the problem says right now at this point in time, HI has an equilibrium concentration. I shouldn't have said equilibrium. It has a concentration right now of 0.01, and I'm going to square that. And then down below, H2 has a concentration right now of 0.005. And then we multiply it by the concentration currently of I2, which is 0.015 molar. Now, all I'm going to do is this. I'm just going to put this into our calculator and write down what we get. So for this, what we are going to do is we are going to take 0.01 and we're going to square it, and then we are going to divide it by, I'm going to do a double set of parentheses, 0.005 times 0.015. Now what I get is 1.33 repeating. I'm going to write down 1.33. And so we have this, and I'm going to rewrite this. Our QC at this point in time, our QC is 1.33. Our KC of this equilibrium expression is given in the problem as 50.5. Now, all we have to do is compare these two numbers. So our QC, which is 1.33, is much, much, much smaller than our KC. So the scenario that we have in this particular example is QC is less, much less, than our KC. So if you take a look back on that previous page, if you see Q, if it's less than K, the forward reaction must occur to reach equilibrium. So our answer to this problem is the forward reaction must occur to reach equilibrium. And so, again, the common thing that you'll hear is this, something with a forward reaction. This means that the whole equilibrium is going to have to shift to the right because of that forward reaction occurring. So, we have an idea of what is the reaction quotient. Now we can go up and we can do a little bit more details with K. So I'm going to transition to our next problem here. And this next problem deals with actually pressure. So we can use that Kp. So for this particular problem, we have this. We have nitrogen gas react with hydrogen, and it comes to equilibrium or produces this NH3 ammonia. Our Kp is listed at 1.45 times 10 to the negative fifth, and the partial pressures of H2 is 0.928 and of N2 is 0.432. We want to know what is the partial pressure of NH3 in this equilibrium mixture. Okay, so to be able to solve this, we have to decipher a few things. Number one, it says, hey, equilibrium. So we're going to assume we're at equilibrium. What that means is that at equilibrium, this is the pressure for H2, and this is the pressure for N2. So what I am going to do is this. I'm just going to put a little note here, and I'm going to say at equilibrium. So at equilibrium, our N2 in this particular example is 0.432 atmospheres. And our H2 is 0.928 atmospheres. Now, right now, it said nothing about our NH3. In fact, that is the question. What is the partial pressure of NH3? So because we do not know what it is, we're going to make this our X. Now what we need to do is we need to think about that equilibrium constant expression. So Kp is going to equal the pressure of NH3. I'm going to put that in parentheses, and I'm going to raise it to the coefficient, divided by the pressure of N2 times the pressure of H2. Because there's a 3 coefficient, we need to raise it to that third power. And now we have some things we can insert into this Kp. So we have the expression written. Up top here, it says Kp is 1.45 times 10 to the negative fifth at this particular temperature. So instead of writing Kp, I'm going to insert that value into that location. This is going to be set equal to our pressure of NH3. Now, NH3, we don't know. It did not list. The problem did not give it. So we said that is our x. That is our variable. So we put x, and then don't forget to square it because of that 2 coefficient. That's really important. Now, at equilibrium, the problem told us that we had 0.432 atmospheres of N2. So we put down 0.432. We close the parenthesis, and then we multiply it by the pressure of H2. So we have 0.928, and we must raise that to the third power. So now all we have to do is we have to do a little bit of algebra to find out what is that value, what is that concentration for NH3, or the pressure of NH3 at equilibrium. So all I'm going to do first is I am going to cross multiply this on bottom times this on top. What I'm also going to do first is this. I am going to, because I only have one thing raised to a power here, I'm going to knock that out first. So I'm going to put 0.928 to the third power, and then I'm going to multiply it by 0.432, and I'm going to multiply that by this 1.45 times 10 to the negative fifth. The answer I got is a really small decimal, so I'm going to put it into scientific notation, and I'm going to write this down. I get a value of, I'm going to do some intermediate rounding here. I'm going to write down 5.006 times 10 to the negative 6. This is now equal to x squared. To get x squared by itself, what we need to do is we need to take the square root of both sides. So if you still have this located in your calculator, what we can do is this. We can say second square root, and then we can say second, and this button down here should say answer, and we should get the square root of what we put, or this number right that I'm pointing to. And so we get a number of 2.24 times 10 to the negative third equals x. Now, our x is the pressure of NH3. So 2.24 times 10 to the negative third atmospheres is the pressure of NH3 at equilibrium. All right, so a major thing here that I want to emphasize before we leave is this. This stated, the problem stated that we were at equilibrium. That's why we could plug these numbers directly in, and that's why we could assume that we have an x, or we have this value we don't know at equilibrium. Key thing here, it is at equilibrium. I know I said that a lot, but that's really important because a scenario is going to change here in just a second. So in this particular last problem, we go a little bit further and we do a little bit more with our K and our equilibrium constant expression, and that is this. we have this equation that we've seen over and over again, and we have a unique circumstance. So what happens here is this. It says a flask is filled with 1 molar H2 gas and 2 molar I2 gas at this particular temperature. We go through the reaction, which we've done this problem quite a few times, and we find our Kc to be 50.5. From this information, we need to know what are the equilibrium concentrations of H2, I2, and HO in moles per liter, which is simply just molarity, big M. So we have to do a lot of work. Notice here it says a flask is filled. I'm going to make a note up top here. Hey, this is another word for saying we have initial values. We don't have values at equilibrium. So what that means, whenever we're given initial values, we have to use that ICE chart. So with our ICE chart, we have this. Initially, we had 1 molar of H2. So for our value here for H2, we start out with 1 molar of H2. Initially, there are 2 molar of I2. Now, that is those things put into the flask, or right before they're getting ready to be put into the flask together. So what that means with our HI is that we have nothing. We don't have any starting material because this business over here on the left has not got to react to produce this. We now look at what we have. We have a Kc, which we've calculated before, but we have to think, do we have a change? The last time we had this type of problem, I gave you one of the change, or we were able to determine one of the changes. This time, we do not. So we have to insert some variables. We start out here with this. We are going to have to lose some of this stuff because it needs to be able to produce some of this stuff. So what that means is we have to have a loss, or a subtraction sign, a minus sign there, and we lost some amount that we don't know. Now, I only put a single x because we have a coefficient of 1. Over here, we have a coefficient of 1. We had to lose some of the I2 to be able to make some HI. So again, we put a minus sign, an x. We put 1x because of the coefficient out in front. Now we get to our products here, or our original products, HI. Remember, we started out with 0, so we can't get any more negative. That means we have to gain, or we have to add some amount of HI. Now the variable that we've been using is x, which we'll use that, but it's going to be 2x, and that is because we have a coefficient of 2. So now we get down to at equilibrium. At equilibrium, our H2 is 1 minus x. At equilibrium for I2, we have 2 minus x. And then at equilibrium, we add 0 plus 2x. So we get 2x. Okay, typically what we would do, and we are going to do it here in a second, we plug the equilibrium values into our expression. So let's go ahead and write the equilibrium constant expression, Kc. Kc is going to be the concentration of HI raised to that second power because of the coefficient of 2 divided by the concentration of H2 raised to the first power times the concentration of I2 again raised to that first power. Now, what I'm going to do is these equilibrium values that are listed right here, I am just going to insert this into what we just wrote down. So we start out with 2x because it's HI. We take 2x and we square it. Down below here, we have H2. Now H2 is 1 molar minus X times 2 molar minus X. What we're going to do, we're going to do a little math, we're going to do a little foiling back to algebra, and what I'm also going to do down below here is instead of putting Kc, if you read in this particular problem, we are given Kc. So Kc is 50.5, and now this is where I'm going to do a little math. On top, 2x squared. If we go through the mathematical operations of 2x squared, we end up with 4x squared. Now, on bottom, I'm going to get rid of these m's because I think they're starting to be confusing. On bottom, what I'm going to do is this. I'm going to FOIL like we would do in math, and I'm going to use a couple different colored pencils so we don't get completely lost in the sauce. So, number one, we are going to do this. We are going to take 1 and we're going to multiply it by 2. So we end up with 2. And then I'm going to do our outers here. So I'm going to take this 1 and I'm going to multiply it by negative x. So we get 2 minus x. And then I'm going to do the same thing here with my i's. Or not my i's. How about my x's? I'm going to do my inner, which is 2 times negative x. That gives us negative 2x. And then I'm going to multiply this negative x times a negative x. That gives us plus x squared. So what I'm going to do from here is this. I am going to simplify this stuff here on the bottom. So I'm going to take 50.5 and I'm going to set it equal to the stuff on top, which is 4x squared. And what I'm going to do is this. I'm going to move this x squared out in front. There's no other x squared on bottom. So I'm going to have x squared minus a negative x plus negative 2x gives us negative 3x plus this positive 2. So what we have to do now is we have to do a little cross multiplication. So what I'm going to do is I'm going to multiply everything that I have here by 50.5. So I'm just going to cross multiply and set it equal to our 4x squared. So 50.5 times x squared gives us 50.5 x squared. 50.5 times a negative 3. I'm going to double check myself on the calculator. Gives us 151.5. So that's minus 151.5 plus 50.5 times 2 plus 101 is set equal to 4x squared. we now run into a problem. The last time we had x squared, we just square rooted everything and everything was fine and dandy. However, and I forgot an x, the x should be right here. However, we have both the terms x and x squared. So what we are going to have to do, it's a little bit of bad news bears, but just a little bit more work, is we're going to have to do this. Number one, I am going to move our 4x squared over to this left-hand side. So I'm going to subtract 4x squared from both sides. And what I'm going to do is this. I am going to end up with 46.5x squared minus 151.5x plus 101 equals 0. Now, this may start to look familiar. Once I get everything to the one side of the equation, what I can do is the quadratic formula to solve for x. This should start to bring back some good algebra memories. So the quadratic formula is x. X is equal to negative b, that's a b, plus or minus the square root of b squared minus 4ac. This is all divided by 2a. Now, our a's, b's, and c's, what they are is this. Our a term is always associated with the x squared. So this right here with the x squared is our a. Our b is going to be the term associated with the x, and then our c is our term with no x at all. So what I'm going to do here, I'm going to grab another sheet of paper and I'm going to use these values and plug it into our quadratic formula to solve for x.